14 of these theories have their own crazy games and terminology of calling the people. So 14 of neutrino, etc., etc. Every particle would have a supersymmetric particle. So the contents would double up. What is the advantage of doing it? If I calculate the self-energy diagram of a Higgs particle, the Higgs boson, it's quadratically divergent in my standard model. Now I do the same in a supersymmetric standard model. I get one additional Feynman diagram. Here, as the Higgs travels, in the earlier one, Higgs travels, it emits a boson, a W particle, W boson, and it reabsorbs. This is Higgs self-energy. Here, while traveling, Higgs splits into a Bino and a Higgsino. And then later on, the two combine to again give you a Higgs. So this is additional diagram. The two are quadratically divergent, but with an opposite sign. So the two cancel each other. So our expectation is now correct. If we increase the symmetry, you get more advantages. So if I introduce supersymmetry, I get the advantage. Some otherwise present divergences, they start cancelling. So in field theory, in standard model, we have to calculate this renormalization of charge and mass and so on to make the cancellations of. So there are three fundamental diagrams called electron self-energy, photon self-energy, and vertex correction. With the help of that, we construct higher order diagrams, and we also calculate, if we have time, sometimes I can make an explicit calculation that the electron and the bare mass and charge of the electron can be correlated with the physically observed mass and charge of the electron, and so on. So this is beautiful. But now, what happens that as soon as I construct a supersymmetric standard model, gauge symmetry gets lost. So the theory becomes gauge non-invariant. Now, if you calculate the constraints of the theory, they would be second class. In the gauge invariant theory, they always follow a set of first class constraints. We have verified it in several examples. It's gauge invariant theory is associated with set of first class constraints. Gauge non-invariant theory with set of second class constraints. Because things start getting difficult, therefore people don't worry too much about it. But that is the fundamental way of doing it. So, if I introduce supersymmetry into my standard model, gauge symmetry gets lost. Then how would I observe the conserved charge? How would I predict the conserved charge? It would be conserved charge, but this would not have any physical meaning or physical significance. This conserved charge has a physical significance only and only if it follows from the local symmetry, local gauge symmetry. Okay, so we again try to walk further. We go beyond the hilltop restaurant, okay, towards the blackboard. We go a little bit, few steps further. यहाँ तो श्रृंखलाएं चलती रहती है पहाड़ों की और आगे चलते रहिएगा, डरना नहीं है. So what happens now? I would like to restore back my gauge symmetry. This I do in two different ways. I make my coordinate system as a curved space-time manifold, so the gravity automatically comes into the picture. Let me briefly recap. How does one construct a theory of QED? In quantum electrodynamics, I can either have a complex scalar field, its kinetic energy, d mu pi star. Now, how do I construct a quantum theory? What do? I replace, there is a standard procedure called as Neodor's procedure. आप लोग लिखिए, Google में देखिए. Neodor, this was Shivaji Bhuman physicist. Emil Neodor, Shivaji Bhuman physicist. She did a lot of fundamental work, and my friend Yuta Kunz from older group, she is also a Bhuman physicist. She always complains that this woman, Emil Neodor, did not get the recognition that she deserved. Nowhere near what she deserved. So this is called Neodor's procedure. You replace your derivative by a covariant derivative. In the process, you introduce a gauge field. Then this gauge field is non-dynamical, so you introduce a kinetic energy. Now, because she considered too many models here, but this is what she was doing. I was trying to read. I looked at these things after a long gap. that she did introduce kinetic energy for that photon, minus 1 by 4 g f while introducing the gauge field. So this is the standard process. Now what do I do for my standard model? I replace the d mu by a super covariant derivative. In the process, I introduce a new gauge field. That new gauge field is a spin 3/2 gauge field. This is called as gravitino. It's a new thing. So far, obviously, no experimental verification, but maybe in future, some students like you might come up. You don't always have to look forward to CERN LHC. It will take, I don't know how many more years to update it with more and more higher and higher energies to be able to detect many things and detect supersymmetric particles. No. I have a friend in Groningen. He's an Indian. Anupam Majumdar, very well-known general relativist. He is conducting, along with some other collaborators, he is conducting a tabletop experiment to experimentally discover graviton. Graviton is a spin 2 particle. It's a spin 2 particle with helicity either +2 or helicity -2. So, this gravitino has a helicity or spin +3/2 or -3. Then you have particles with vector-like particles like photon or W plus minus, or they are all vector kind of particles. So they are called vector gauge bosons. So the spin is either +1 or -1 for a photon. Okay, helicity is either +1 or -1. And then fermions, electron-type particles with spin +1/2 or -1/2. Then the unique Higgs boson, which has spin 0. So now I would tell you how our understanding advances with the introduction of new and new ideas. Let me first consider the standard model and its supersymmetric generalization. When I introduce supersymmetry, so in terms of mathematical description, you have the transformation, gauge transformation parameter becomes fermionic. And how many of such parameters you have in your theory? Supercharge, there is something called as supercharge, which is proportional to the transformation, gauge transformation parameter, which is fermionic. So obviously supercharges are also fermionic. Now one supercharge can annihilate a state to produce another state with helicity reduced by 1/2. So in n equal to 1 supersymmetry, I would have, let us say, one photon. The particle with highest spin is a photon in standard model. Okay. In gravity theory, I would tell you that the particle with highest spin is a graviton with spin +2. So if I consider just without gravity, standard supersymmetric standard model, a photon with spin 1. If I consider a massless system, then photon neutrino system. Then I annihilate it with the supercharge. I will have a state with spin 1/2, which is 1/2 reduced from 1. एक में से आधा घटाइए, आधा बचा. देखिए, अगर आपको कोई समझाने वाला अच्छा हो तो छोटा बच्चा भी धीरे धीरे बहुत टॉप की चीजें समझ सकता है. समझाने वाले की जरूरत है, समझाने वाले की जरूरत है. ठीक है, समझाएंगे और आप समझने की जरूरत. आप इफ यू वुड ट्राई टू अंडरस्टैंड व्हाट आई एम टॉकिंग, रिपीटेडली आप एफर्ट्स करेंगे, मैं भी आपको रिपीटेडली एफर्ट्स करके समझाऊंगा तो बड़ी बड़ी चीजें समझ आ जाएंगी. समझ गए? ये आप भरोसा रखिए और इसी उम्मीद के साथ आप आगे पढ़ाई करते रहिए. जितना टाइम यहाँ मिलता है टीचर से लर्न करने का करिए, नहीं तो आजकल इंटरनेट है, गूगल आपके मोबाइल में है, बस घर बैठ के कुछ कुछ देखिए. आपके यहाँ पर कोट लिखा हुआ है, विद्यार्थी जीवन में ही अधिक से अधिक ज्ञान को अर्जित करना है. ये फाउंडेशन है. Unless you make the foundation strong, you cannot build a building. है? तो ये अगर मैं n equal to 2 सुपरसिमेट्री करूंगा तो एक फोटोन अब 2 सुपर चार्जेज होंगे, एक बार फिर 2 बार, तो मेरे पास 2 न्यूट्रॉन आ जाएंगे. दोनों को इकट्ठा कर दूंगा तो एक स्केलर पार्टिकल भी आ जाएगा. तो वहाँ मैक्सिमम अलाउड सुपरसिमेट्री n equal to 4. So I start with a photon with spin 1, then spin 1/2, then 0, then -1/2, then -1. So a photon with spin +1 and a photon with spin -1, and in between. Its numbers can be calculated: 4C0, 4C1, 4C2, 4C3, 4C4. Now I do the same exercise in a supergravity theory, a theory which contains not only a standard model, not only a supersymmetric standard model, but including gravity. So I make my space-time curve and I introduce supersymmetry, and I try to make a global supersymmetry, which is a rigid supersymmetry. The transformation parameter is a constant spinor. I make it a function of x nu. You might find these ideas difficult. They are even difficult for me. But कुछ याद रहेगा तो आप आगे कुछ न कुछ आपको इच्छा होगी क्या बोल के चलेंगे सर, हम देखते हैं. You will be able to discover it in your mobile phone, many things, and you will gradually advance towards better and better understanding. So similarly, I can have in supergravity theory, which is called the supergravity theory. I would have in n equal to 1 supergravity theory. There is one graviton with spin +2, one supercharge. It annihilates once. I get a spin 3/2 particle, which is called gravitino. So one graviton, one gravitino. If I have n equal to 2 supersymmetry in supergravity theory, this is Einstein's ring theory. You have 2 supercharges. You annihilate your graviton state once, you get one gravitino. You annihilate it again, you get second gravitino, 2 gravitinos. If you annihilate by both of them, then you have a spin